Welcome back to HackCode. In this video, we're tackling an essential problem for coding interviews, rotate image from LeetCode. This problem is great for learning matrix manipulation and in-place operations. We'll explore two approaches, brute force and in-place rotation. Problems like this are often asked to test your analytical thinking and logical building skills rather than focusing on data structures. Let's break down the problem step by step and understand how the solutions work. So sit back, relax, and let's dive in. So what is the problem statement here? You are given an n-cross n2D matrix representing an image. Rotate the image by 90 degrees clockwise. So basically we need to rotate this n-cross n matrix 90 degrees in clockwise direction. So if you're not already aware, a digital image is a 2D array of pixels. So here we can see that a digital image is a 2D array of pixels. Each pixel is characterized by its xy coordinates and its value. Basically an image consists of pixels. And here, as we see, each pixel has its own value and its coordinates are represented as xy in this 2D matrix. This is just to give you a real world idea of how the image is so that you can correlate with this problem, okay? And they mentioned that you had to rotate the image in place, which means you had to modify the input 2D matrix directly. Do not allocate another 2D matrix and do the rotation. So basically they mentioned that we had to perform this transformation in place. That means that we should not use any extra space to achieve this. But we'll explore extra space and in-place operations. Don't worry about that, okay? Let's look into examples here. So basically, first example is given as 1, 2, 3, 4, 5, 6, 7, 8, 10. This is stands up to 7, 4, 1, 8, 5, 2, 9, 6, 3. So how did we achieve this transformation? So if you see this matrix, this is the given. So we just rotated it 90 degrees in clockwise direction. So for example, I'll just do in front of you here. So if we have this and I just rotated it 90 degrees clockwise. So that's how we got this one. So we just put this in a good format here. I mean like proper format 7, 4, 1, 8, 5, 2, 9, 6 instead of this rotated numbers. Okay. So this is the point from where we count our row and column indices. Okay. So this is the 0th row, this first row and second row. This is also 0th first and second column respectively. Okay. So here, how is the transformation happening? So if you take the example of 3 here, so previously its coordinates are what? 0, 2. It's 0th row and second column. Now, how is it transformed? It is transformed to 2, 2. That means that whatever we have for the column is now becoming row index, right? And now this is something we have to calculate. So how can we achieve this from this one? So here n is equals to 3, right? So this is what 3 cross 3 matrix, that's why n is equals to 3. So now how did we achieve this? So here a new j is equals to, or new column it is, we can say n minus 1 minus I. So I is what? Previous row index. So n minus 1 is what? 2 minus I is what? Its previous row index. It's what? 0. That is 2, right? So this is a simple observation we have, right? So that is how we got this 2, 2. So similarly for 4 as well. So 4 previously it was what? First row and 0th column. Now it is transformed to 0th row and first column. Okay, so basically this is straightforward. So column is now becoming as a row index, and this is what something tricky, right? So this is the formula we have for achieving this one. Like we just formulated it by the observation, nothing fancy here. N minus 1 is what? Most valid index we have, and we are just subtracting I from it. So n minus 1 here in this case what? 2. And then what is the I? 1. 2 minus 1 what? 1. That's how we got this. So the generic formula is j n minus 1 I. So if you do not get this idea, don't worry, we'll look into a practical example now. Okay, so let's take this. So basically what's happening in this case also, this particular column is getting transformed into this particular row. Okay, so let's collect these two and take a deeper look. How are we achieving this transformation? So here old list represent the form when it was in the column. So new list represent the format when it is in the row. So basically here the column is transformed to row, right? So that's how the representation is made here. And here I'm just enumerating over the new list and then printing the index and its value. So here new list of 0 is equals to 15, and similarly we have new list of 3 is equals to 5. So how can we correlate these two numbers or these two indices? Okay, so that is just like I and n minus 1 minus I, right? So here if you see, when old index is 0, what is the element we have? 5. When new index is 3, what is the element we have? 5. So basically we can straight away say that n minus 1 minus I is the formula we can achieve by just observation. Okay, so that's how we get, and this is the formula we have for new indices. Okay, so before we dive into the code, let's look at the boilerplate code given. Here we have a rotate method which takes the list of integers, that is a matrix here, and returns none. So basically here we do not return anything and modify the matrix in place. Okay, before we get started, I want to remind you about our exclusive blind 75 post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FAANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. So now let's look into the approaches. So first approach is brute force. Okay, this is of O of n square time and O of n square space. What is the intuition? In this approach, we use an auxiliary matrix to store the rotated version of the original matrix. For each element at position ij in the original matrix, we place in its rotated position, that is j n minus 1 minus I in the new matrix. Okay, this is the intuition here. Okay, so basically this we discussed, right? How do we arrive at this? Okay, and after this what we do, we just copy back this to the given matrix so that our given matrix would have the cells in the rotated fashion. Okay, so now let's look into the algorithm. So first step is obviously to create a new matrix to show the rotated version of the original matrix. So basically this is to create the n cross n or whatever the given dimensions we have. Okay, for that dimensions we have to create a new array, and the next step is to iterate to the each element in the original matrix. So after iterating, what we should do, we should place the each element at its rotated position in the new matrix. Okay, so this is just like having our new matrix in a rotated format of the given matrix. And then step 4, we copy the new matrix back to the original matrix. So this is how we making our original matrix to be a rotated matrix, by just copying the cells from the new matrix we created. So let's look into the code. So firstly, what we are doing, we're just getting the length of the matrix. Okay, so here it's an n cross n matrix, so that's why the row and column are the same length. Okay, and step 1, we create a new matrix to store the rotated version. So for that, we are using the list comprehension approach. So if you don't get this code, don't worry, I'll give you a closer look into that. So now here I just took n is equals to 4, and what I'm doing here, multiplying the list of 0 into n. So what will this give? So this is giving us list of length 4 filled with all zeros. Okay, so now in the next step, what I'm doing, I'm just taking this and then repeating for n times using a for loop. So let's execute this. We get a n cross n matrix filled with all zeros. Okay, so this is the list comprehension way of forming a 2D array. Okay, so now we initialize our rotated matrix and all cells are 0. Okay, the next step is to iterate to the given matrix. Okay, so for that we require the 2 loops, right? So basically we have row and column, and then each has its own pointer. That's why we have the 2 loops here. So we just iterating the each element in the original matrix, and then we place each element at its rotated position in the rotated matrix. So how can we achieve that? For each ij in the original matrix, we just place them in our j n minus 1 minus I position in the rotated matrix. So that's how our rotated matrix holds the rotated version of the given cells. Okay, in step 4, we copy the rotated matrix back to the original matrix. So that's how we make our original matrix to be a rotated matrix. So for given ij, we just filling it with the rotated matrix of ij. That means that whatever there in the rotated matrix, that would be copied back to our original matrix. Okay, simple, right? So now let's look into the complexity. So time complexity is O of n square, as we are iterating over each element of the original matrix and making a copy. So here it is n square and here it is n square. Okay, so total it is 2n square, but 2 is negligible factor, so it's n square. Okay, so space complexity is also n square, since we are using an auxiliary matrix of the same size as the original. So basically, if the given matrix is n cross n, we are forming a same n cross n matrix as a rotated matrix here. So that's why it's n square. Okay, so I got the code ready here. Let me try running this. So this accepts the solution for the 2 cases. Let me try submitting this. So this is the accept solution for all the test cases. Okay, so let's look into this in place rotation. So firstly, we have this original matrix. What if we perform a transpose on this? So basically, what is transpose here? If you're not aware of what is transpose, a transpose of a matrix is an operator which flips the matrix over its diagonal. That is, it switches the row and column indices of the matrix A by producing another matrix, often denoted by A transpose. So let's look at an example here. This is the original matrix A. If we transpose it, that means we flip over this diagonal, we get a transpose. Okay, so basically here cells are flipped over this diagonal, and then if we perform the transpose again on it, we'll get a back. So the property here is A transpose co-transpose is A. Okay, so this is just the basics to give an idea. So you got the idea, right? What is transpose? We just flip over the diagonal. So if we take this diagonal, we just flip over the diagonal. That means that this 4 2 we have, right, that would become as 2 4. Similarly here we have 7 3, that would become as 3 7, and then we have 8 6, which would become as 6 8. So this is the transpose matrix. Now how far is transpose matrix from the final matrix? This is the final matrix we require, right? So if you look into these two, we can say that this row is reversed here. So basically, after doing a transpose, we just need to reverse this row. Okay, then we achieve our final design matrix. Okay, so basically this is a 2-step process. Firstly, we have to transpose the matrix, and then we have to reverse each row. That's how it is. Okay, so let's look into the intuition. So instead of using an extra space, we can rotate the matrix in place by following two main steps. Firstly, transpose the matrix, that is swap the rows and columns. Next is reverse each row. This gives the desired rotation without using additional space. So we just discussed the intuition over here, right? So now let's go to the algorithm. Step 1, transpose the matrix by swapping matrix ij with matrix ji. So how can we say that? So if you look into the given matrix, this is the diagonal. So let me just represent the indices of row and column. This is 0, 1, 2. Okay, this is basically for row and this is for column. So here, what are the indices of the diagonal elements? So it is 0, 0. So for 5, it is 1, 1. And for 9, it is 2, 2. So if we pick this as I, j indices, what can we say? I is equals to j, right? So in that case, we can generalize this as I, I. So we don't need to swap these diagonal elements. We just need to swap the elements which are non-diagonal. That means that we can represent this non-diagonal elements as matrix of I, j. Okay. So we just need to swap this I, j with what? Matrix of j, I. So that is the transposition, guys. Okay. It's just a basic observation. And here we just need to swap these two elements, these two elements, these two elements. Okay. Step 2, iterate to the each row and reverse it to complete the rotation. So basically after transposition, we have to reverse the each row to get the final matrix, right? So that's what we have to do in the step 2. So let's look into code. So firstly, we're getting the length of the matrix in n. Okay. And then next is we doing the transposition of the matrix. So for that, we're using the two loops. Obviously, we require two loops because we have to iterate over the row and column. Okay. So what is the range of rows we are iterating here? So rows will be in the range of 0 to n minus 1. Okay. So this is the standard index range, and columns would be in the range of I plus 1 to n minus 1. So why I plus 1? So basically I is what here? Our current row. So for the current row, we are accessing I plus 1 column. So why is that required? So let's look into case where I is equals to 0. So I actually ranges from what? 0 to 2. Okay. So this is the range. So when I is equals to 0, what are the j values possible? 1, 2. Basically j ranges from I plus 1 to 2, right? So that's why it is 1, 2. So what are the coordinates we'll be getting here in the matrix? It is what? 0, 1 and 0, 2. So these two values, right? So these two values will be getting, and we will be swapping this with what? This value and this value. So these two values will be swapped. So after this, we have I is equals to 1. So for I is equals to 1, what is the possible value of j? It is just like 2 only. So only coordinate we'll be getting is what? 1, 2. So 1, 2 is what? This one. So this would be swapped with this one. So we are done, right? So basically we just need to access the upper diagonal elements, and we need to swap this with the lower diagonal elements. So that's why we just need our j from I plus 1 to n minus 1. Okay. So that is the condition we have in the for loop here. So hope you got the idea, and this is the pretty standard tuple unpacking way of swapping these two elements. Okay. So if you choose an extra variable, then this is how you'll be swapping. Temp is equals to a is equals to b is equals to temp. So this basically is circular swap. Okay. In step 2, we just need to reverse each row. For that, we're using only single for loop. Why? Because each element in the matrix is what? It's a single row, right? So if you take this matrix, this is a list of lists. So each list here represents what? A row. So if you take 5 or 9, 11, it is a row here. And if you take 2, 4, 8, 10, this is another row here. So basically, each element in this outer list is a row. So we just need to access that element, and that element is our list. So for that list, we have to reverse. So that's why we're using a single for loop here to reverse this. So here matrix of I gives the row, and then we are applying the dot reverse method on it. So basically dot reverse the row in place. Okay. So if you don't have idea on dot reverse, let's look into that in action. So basically we had temp is equals to 1, 2, 3, 4, and if you do a reverse on the temp, what will the temp will be like? So temp will be 4, 3, 2, 1. So this is happening in place. Okay. So what if you do colon minus 1? So it generates a new list. It doesn't change in place. If you access a temp, it will be still 4, 3, 2, 1. So this generates a new list, and this is the in place operation we have. Okay. So that's why we use the dot reverse, which reverse the list in place. Okay. So let's look into complexities. Time complexity is O of n square. As we are iterating over the matrix twice. Firstly, we're iterating for transposition, and next for reversing each row. So here it is n square, right? So let me just put into the literal terms here. So firstly, we're getting in for range of n, and next we are doing in the range of I plus 1 to n. So when I is equals to 1, it is like from 2 to n. So basically it would be one less element from I. So it is what? N square minus n. So that's actually n, because this is negligible. And here also we're going it for n times in outer loop. So within the loop, what is happening? Matrix of I dot reverse. So this reverse method, this time complexity is what? N. Basically it has also to iterate over the each element to reverse it, right? That's why it's n. So here This is n into n square. So totally it is 2n square, and 2 is negligible, so it is n square. Okay. The space complex is O of 1 since we are performing all operations in place. So guys, if you look here, we're not using any extra space which grows with the size of input. We are just changing the matrix which is given only. So it is O of 1. Okay. So I got the code ready here. Let me try running this. So this accepts solution for 2 cases. Let me try submitting this. So this accepts solution for all the test cases we have. Okay. So congrats guys, you just learned 2 different approaches, brute force and in-place rotation. As I mentioned before, this type of questions would be asked only to test your logic building skills. Okay. So this is very easy. You just need to do a careful observation. That's all. Okay. And that's a wrap on solving the rotating image problem using 2 different approaches. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit that subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. See you in the next one.